Good morning. Happy Monday. I think I forgot to tell you all that I wasn't going to be here today. I'm at a conference learning about SAT material, how to prepare for it since it's a graduation exam. But regardless, we are going to move on. You will have homework, so make sure you're taking the notes and doing what we need to do. Today we're going to start with binomial and geometric random variables. It's a pretty long unit. We are just doing binomial today. So our learning target is, I can determine whether the conditions for a binomial setting are met. I can calculate and interpret probabilities involving binomial distributions. I can calculate the mean and standard deviation of a binomial random variable and interpret these values. A binomial setting arises when we perform n independent trials of the same chance process and count the number of times that a particular outcome called a success occurs. The four conditions for a binomial setting are binary. The possible outcomes of each trial can be classified as success or failure. So there's two options, success, failure. Independent. Trials must be independent. That is, knowing the outcome of one trial must not tell us anything about the outcome of another. So the first trial does not affect the second trial. The number of trials in of the chance process must be fixed in advance. So there's 5 attempts, there's 10 trials, there's whatever. It has to be fixed. Same probability. There's the same probability of success P on each trial. The first letter of the bulleted points give you a helpful way to remember the conditions by binomial. You check BINS, B-I-N-S. So hopefully that helps you remember how to check. I know we have a lot of acronyms. Determine whether the given scenario describes a binomial, and then justify your answer. Genetics say that the genes children receive from their parents are independent from one child to another. Each child of a particular set of parents has a probability of 0.25 of having type O blood. Suppose these parents have 5 children. Count the number of children with type O blood. So let's start checking BINS. Binary. Are there two outcomes, success, failure? So yes, the success would be type O. A failure would be not type O. N, are they independent? And they are yes. Whatever the first child is should not affect what the second child is. N, number of trials, and there are 5 because we're having, suppose these parents have 5 children, so each child is a different trial. And same probability is a yes, and it's 0.25. So this is a binomial setting. And that will become important because we need to know what type of probability method to use. So knowing that it's binomial is important. All right, shuffle a standard deck of playing cards. Turn over the first 10 cards one at a time. Record the number of aces you observe. So binary is our first question. Success is an ace. A failure is no ace. So we've got binary. Independent. No. Because it says turn over the first 10 cards one at a time. So I'm turning over the first, then turning over the second. So I'm not putting the first one back. So no, since there's not replacement, and I can stop as soon as I get one no. So this is not binomial. Shuffle a deck of cards, turn over the top card, put the card back in the deck, and shuffle again. Repeat this process until you get an ace. Count the number of cards that you had to turn over. So let's go through the bins. Binary. We're just going to talk about it. Yes. So turn over the top card, put the card back in the deck, repeat this until you get an ace. So same thing, success is an ace, failures, no A's. Independent is now a yes, because I'm putting the card back. And then we have a number, which is 10 cards, I believe. Oh, I am so sorry. Here we got a no. I apologize. Looking at the wrong thing. Repeat this until you get an ace. So the number, we don't have a fixed number because I'm going to keep going. I don't know if it'll take me 5 times to get an ace, 4 times, 1 time, 20 times. So this is also not binomial. Okay, now you have a couple of checks for understanding, your tries. So read through them, give me an answer. If you don't understand, we'll discuss them on Monday. So this will be, or Tuesday, this will be a good thing for us to do if you don't understand. So you'll have to pause here, answer before the video will move forward. So A is a yes, it is binomial if you didn't get that. It's binary because I'm rolling a fair die 10 times, and we want X to be the number of sixes. So a 6 is a success, a no 6 is a failure. Independent, a fair die, whatever I get on the first does not affect the second one. Number, doing it 10 times, and probability is 1/6 every time, so that's a yes. For B, it's a no. Shoot a basketball 20 times from various distances on the court, let Y be the number of shots. Well, you could say yes to a couple things, but the probability is not the same if you're moving to from different spots on the court. Obviously, shoot a layup, it's a higher probability than if you're hitting a 3-point shot or whatever. So this is a no, the probabilities would not be the same. And don't forget, just one no makes it not binary. So you should have gotten no there. All right, next set, we're going to actually figure out the probabilities. The blood type scenario in the example above or on the previous page is a binomial setting. If we let X equal the number of children with type O blood, and then X is a binomial random variable. The blood type scenario in part A of the example is a binomial setting. If we let X equal the number of children with type O blood, well, that sounds very familiar. I think I need to delete that. All right, the count of success X in a binomial setting is a binomial random variable. The possible values of X are 0, 1, 2, ... to n. The probability distribution of X is a binomial distribution. Any binomial distribution is completely specified by 2 numbers. Excuse me. The number of trials n of the chance process and the probability p of success on each trial. Suppose that X is a binomial random variable with n trials and probability p of success on each trial. The probability of getting exactly k successes in trials k equals 0, blah, 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 is the probability of X equals k. And here's the formula. It looks confusing, but it's not. I'll talk about it. In k, that's really just a combination. I usually see it written like that. The probability of n things taking k at a time. But in statistics, they'll write it with that notation in those parentheses with n over k, but that's just a combination. P is the probability of success, so it's the probability of success raised to how many successes you want. 1 minus P is the complement. I lots of times call it Q. In regular stats, they'll call that Q. So if you catch me doing that, you know that 1 minus P and Q are the same thing. So it's the probability of a failure, and it's raised to the power of not getting the success. So K and N minus K obviously have to add up to be the total number of trials. And then if you've forgotten, the combination formula from Algebra 2 or wherever you learned it is that formula. So let's use it. Genetics says that the genes children receive from their parents are independent from one child to another. Each child of a particular set of parents has a probability of 0.25 having type O blood. So the same as before, we were looking at these parents have 5 children, let N or X equal the number of children with type O blood. So the probability of X equals 3. So here's what we need so we can substitute into that formula. N is 5, P is 0.25, so 1 minus P is 0.75, and K, or X in this case, is 3. So when I substitute in here, I'm going to do 5 factorial over 3 factorial, 5 minus 3 factorial, times 0.25 to the third power times 0.75 to the second power, which equals 10 times 0.25 to the third times 0.75 to the second, which equals 0.00, oops, I put an extra 0, 0.088. Now let's make sure you know where those numbers came from. If you go back to your calculator, a couple of things you can do. If you want to type in the 5 factorial, you find the factorial key under math. I don't know what, there it goes. Under probability. So 5 factorial is right there. Divided by parentheses 3 math factorial, parentheses, 5 minus 3 is 2 math factorial, close those parentheses. There's the 10. The 0.25 was the probability of success, and I wanted 3 successes. 0.75 is the probability of failure. If there was 3 successes, there had to be 2 failures. We'll come back to the calculator. I'll show you some other things in a moment. Now to interpret this for time, I'm not going to write it down in space, but you probably need to. There is about an 8.8% chance that 3 out of the 5 children have type O blood. Easy as that. Should the parents be surprised if more than 3 of their children have type O blood? Calculate an appropriate probability to support your answer. So for this one, I want the probability that X is greater than 3. So that's the probability of 4 plus the probability of 5, which is going to be 5, oops, I'm going to do it their way. I'm just going to write it like this, and I'll show you in just a second. 5, 4, 0.25 to the 4 times 0.75 to the first. Because if I have 4 successes, there's only 1 failure. Plus 5, 0.25 to the fifth. If all 5 of them are, then that means 0 weren't. So a shortcut, and then I'm going to show you other shortcuts in a minute. To do that combination, you can also go to Math, Probability. Option 3 is Combination, and I can put in 5, combination 4. And so there are 5 ways that out of the 5 children, 4 of them could be type O. And you could type that all in your calculator, and you would get 0.015. And I'll show you how to do that tomorrow if you have questions about your calculator. So can you support this? It says yes, there's only a 1.5% chance of more than 3 children having type O blood. You can do this whole thing in your calculator. You will have, I promise, some multiple choice questions or some places where you have to understand the formula for binomial, but if it just asks for the probability in a free response question, you can use your calculator. And I've got screenshots there. Binomial PDF is if you want exactly one thing to happen. Exactly 3 of the kids had type O. If you want it to be greater than or less than, you're going to use the CDF. CDF is automatically less than or equal to the value you put in. So if you want less than or equal to, you just do it straight up. If you want greater than, you're going to have to do the complement. We'll look at a couple of those in a minute. How to find binomial probabilities. Step 1, state the distribution and the values of interest. Specify a binomial distribution with the number of trials n, successes p, and the value of the variable clearly identified. Step 2, perform calculations, show your work. Do one of the following. Use the binomial probability formula, or use binom CDF or CDF, and label each of the inputs. Be sure to answer the question that was asked. Example, a local fast food restaurant is running a draw 3, get it free lunch promotion. After each customer orders, a touchscreen display shows the message, press here to win a free lunch. A computer program then simulates one card being drawn from a standard deck. If the chosen card is a 3, the customer's order is free. Otherwise, the customer must pay the bill. On the first day of the promotion, 250 customers placed lunch orders. Find the probability that fewer than 10 of them win a free lunch. So we're going to identify these parts. N is 250. P is 4 out of 52 because we're trying to draw a 3 and there's 4 3s in the card. And we're trying to find the probability of fewer than 10, which is the same thing as x being less than or equal to 9. So the probability of x being less than or equal to 9 is binom CDF because I want from 0 to 9 to occur. And I don't put 10 in because the binom CDF goes all the way up to the last number you put in. And if a less than 10, 10 is not included. So binom CDF, and I'm going to label, I'm going to do the option 2 up there. The trials for 250. The probability of success was 4 out of 52. And x equals 9. Now let me show you where to go in your calculator to do that. So you're going to go to second distribution. It's way down there. Mine's B, I believe. Yours might be different, but I want CDF. Now if you have the newer version, it prompts you. 250 trials, 4 out of 52, and I want up to 9. It will add those all together for me. It will take the probability of 0 through 9 and add them together. And you get 0.00613. In fact, only 9 customers won a free lunch. Does this result give convincing evidence that the computer program is flawed? So since there's only 0.00613, which is less than 5% chance that fewer than 10 customers win, we have convincing evidence, because it couldn't happen, most likely didn't happen by chance. There's only a 0.00613 chance that it happened by chance, so it must be real. That says computer, by the way, sorry. Computer program is flawed. Because that didn't happen by accident. There's only a 0.00613 chance it would happen by accident. All right, one last little part. On the second day of the promotion, 275 customers placed lunch orders. Find the probability that more than 25 customers. So this time I want the probability that X is greater than 25. So N is 275. P is still 4 out of 52. And X is 25. Okay, I want 25 or more. So here's what I have to do. I have to say 1 minus the probability that X is less than or equal to 25. Because my binomial CDF is going to go up to 25 and I want more than 25, so I'm going to subtract them. So this is 1 minus binomial CDF. Number of trials is 275. Probability of success is 4 out of 52. And X is 25. If you type that in your calculator, you get 0.162. All right, I'm going to stop it here again so you can try these. So you have 3 to try, and we'll come back and talk about them. So on A, I'm just going to jump to the answer. If you have questions, you need to ask me tomorrow. I don't want to make this video too long. So A, he's feeling lucky. We want the probability it's fewer than 20. So that should be 0.0995. Does this result give convincing evidence that the probability of winning is less than 1 out of 4? So 0.0995 is greater than 5%. So we do not have convincing evidence the probability of winning is less than 1 in 4. On C, find the probability that more than, so the probability that X is greater than 15, you're going to have to do 1 minus the probability that X is less than or equal to 15. And I'll show that in the calculator very quickly. 1 minus second distribution. Again, scroll down till you find yours, binomial CDF. This one had 100 trials. Probability was 1/4. And I wanted 15. Point 1, 2, 3, 4, 5, 6, 7, 8, 1, 1. So there's not a very good chance that the probability that they win 15 tickets are winners, that more than 15 tickets are winners. All right, almost there, guys. So to describe shape, center, and variability, if a count X of successes has a binomial distribution with number of trials N and probability success P, the mean is N times P. They also call that expected value. If a count X of successes has a binomial distribution with number of trials N and probability success P, the standard deviation is the square root of N times P times Q, or 1 minus P. Caution, remember that these formulas for the mean and standard deviation work only for binomial distributions. So we have the example. Assume that each of the 21 students in the AP class who did the bottle flip versus tap water activity was just guessing. So there's a 1/3 chance of each student identifying the cup containing bottled water correctly. X is the number of students who make the correct identification. So we have the histogram right. Main idea is that you know that it's normally distributed. That's kind of important sometimes when we're doing this. Calculate the mean. The mean, which is also the expected value, ignore that, X, that should be our mu symbol, equals N times P, which is 21 times 1/3, which is 7. So if all students in Mr. Hogwarts class are just guessing and repeated the activity many times, the average number of students who guessed correctly was about 7. Calculate, determine, and interpret the standard deviation of x. The standard deviation of x is the square root of n p 1 minus p, which is the square root of 21 times 1/3 times 2/3, which is 2.16. So if all students in Mr. Hogarth's class were just guessing and repeated the activity many times, the number of students who guessed correctly would typically vary by about 2.16 from the mean. Pause and try. The mean is NP, which is 28 times 0.5, or 14. So you should say if you toss a coin many times, so basically just like we had up there, the average number of, what are we trying to flip? Landed on heads would be about 14. So the standard deviation is the square root of n times p times 1 minus p, which is the square root of 28 times 0.5 times 0.5, which is 2.646. So you would say the number of times that the student gets a heads varies by about 2.646 from the mean of 14. All right, I missed you all today. I hope you had a great Thanksgiving. You have homework. Make sure you get that done, and I will see you tomorrow.